talk about mechanisms. Now, reaction mechanisms are the actual steps by which a reaction takes place. It can be one step or it can be any number. And each step is referred to as an elementary reaction. And an elementary reaction has particular properties like actuality that none of the other ones do. And I'll show you in just a minute. But the sum of all steps must equal the overall reaction. Okay, so the rate of the reaction is determined by the slowest. And this actually makes sense because if you think about when you have a series of jobs that one person has to pass to another or do something pass again, the how fast you get done is a function of whichever step is slowest. So that is what sets the rate. Okay, intermediates are species that are generated and used up during a mechanism. Now, I referenced intermediates earlier when I talked about transition states. Transition states are fleeting. You really can't capture them. But intermediates are something that are formed and then used up. So they appear in different steps, but they don't appear in the overall equation. Okay? Catalysts, on the other hand, are interesting because they appear in the overall or the net equation or as both a reactant and a product. Okay, so if you write an equation, A goes to B, and you have Fred would be your catalyst. Okay, but if you had Fred plus A yields B plus Fred, then you threw Fred in, but Fred isn't used up, so Fred is your catalyst. Okay? So when you actually talk about these elementary steps, then you've got to talk about how many you have. Okay, unimolecular, like a unicycle, is one. So it is the rearrangement of a single molecule. And it's actually a very common reaction in organic, etc. Bimolecular involves the collision of two particles. This would be like in acid base where your acid hits the base ionic, they're fast, etc. But if you think about it, these are kind of hard too. If you have one molecule and you're rearranging, you have the molecule where it's at, etc. But if you have two molecules and you have to have them impact with the proper collision, then think about two people in opposite corners of a room throwing baseballs at each other. Now, you get the right people, they can hit just about every time. You make it more interesting by putting dots, big dots, on the baseballs. Now they have to impact and the dots have to hit. It gets much more interesting. Well, termolecular is kind of like a, unicycle, bicycle, tricycle. No, ter is 3 particles. Now, these are not really that common of a reaction because think about it. Let's go back to throwing up the balls from the corner. You're not throwing 2 now, you're throwing 3, and they have to collide with the proper orientation. Now, I am sure we could get a bunch of major league pitchers in and they could make this work, but not everybody or every particle is a major league pitcher. So this is actually kind of hard. So if this is out of your text, if you noticed, they have the molecularity, the elementary reaction, and this is where I did tell you that elementary equations are different because you can actually use what you have here to determine the rate law. So notice we have 2 A's and a B, so this is A times A, remember, is equal to A squared. So this is A to the second B. This is A times B times C. This is AB, AA, etc. So if you have a point of confusion, you may want to take a second and look over this slide here. So the question is which of these are unimolecular, bimolecular, whatever. So if you look at A, this is the reactant side, and that's all we look at. We have one molecule, so it's unimolecular. Okay, instead of doing B, I'm going to go down the column. Okay, here's again our reactant side. So again, it's 1, so it's unimolecular. Okay, on this one, if we take this, we have 1, 2. So this is going to be bimolecular. Okay, again, we take everything on the reactant side. We have 2, so this is bimolecular. And on this one, we have a single. This is definitely a rearrangement, as are the other two. This is unimolecular. So easily, what you look at it, and we're going to look at a written one shortly, but you just look in and see how many particles you have reacting. Okay, this is the mechanism for the oxidation of iodide by hydrogen peroxide. Now, this reaction is in your text. This particular slide is not, because this shows everything. So notice that we have step 1, step 2, and step 3. If I could spell step, we would have them. Okay, so notice we have the hydrogen peroxide times the iodide going to OH minus and HOI. Then the HOI is reacted here with another iodide to form another hydroxide and a full iodide. Then you have 2 hydroxides and an acid form water. So if you add all the reactants together, remember you treat the arrows kind of like equal signs. Don't write them as equal signs, but you treat them as equal signs in math and you add them together. So this is the total sum. Now, just like in algebra, if you have the same species on both sides, you can eliminate it. If you have 4 M's on one side and 2 on the other, then you end up with 2 M's only on one side. Okay? If you have 4 and 4, then they both go away. So if you look at this, we can say that I2 is not the same as iodide, so we don't get that. We have HOI and HOI. That one goes away. We have 2 HO minuses and 2 HO minuses. Okay? So when we eliminate that, look at our net. So what we say about these species is that they're not there initially and reproduced at the end. So they're not a catalyst. So these two are intermediates for the reaction. Okay? So this begs the question, will any reaction mechanism do? Well, let me go back real quick because I forgot something. This is the slow step and the other two are fast. So this is the one that's going to determine the rate. Why? Because we're told it's slow. How do we know it's slow? Because I tell you. Okay, this is not something you should look at and say, oh, that looks like a slow reaction. Or that looks like a fast reaction. No. I have to tell you enough information for you to either be determining which one's slow, or I'll tell you this one's slow so that you can determine if it works. Okay, more about that on the next slide. So back to the reaction mechanisms. The reaction between nitrogen monoxide and oxygen is written there. And you're found to experimentally obey the rate law. So we know this is the rate law. So decide which of the following mechanisms are compatible with this rate law. Well, the first thing we have to do is look at it. And we're going to gently mark through so we can record it. And so we've got 2NO plus O2 yields 2NO2. Okay, well, that matches up here. So far, so good. But on the slow step, that's going to determine your rate law. And for elementary half reactions, that means that whatever is written is written. So according to the slow step, the rate is going to be equal to K times N2O2 times O2. Okay, so let me actually erase that and rewrite it down here. So the rate is equal to K into O2 times O2. And one of you may have said, wait a minute, that intermediate dropped out. Well, it did for the overall reaction. But for that slow step, it's still there. If you remember way back when we first talked about rate laws, there was one where we had a molecule and we threw in iodide in our rate law, and you're like, where did that come from? And I said that the iodide was a catalyst. Well, guess what? Catalysts can take part in the slow step. Anything that takes part in the slow step, intermediates, catalysts, whatever, set the rate. Okay? So this says, okay, this is bad because notice there's no N to O2 in our rate law. Okay? So that was relatively easy. And I'm going to change colors here to help differentiate. So on the second one, we get the N's cancel. So we're 2NO plus O2 yields 2NO2. So this matches. But our rate will be equal to K times NO times NO. And remember, we can write that as K times NO squared. Okay, so we look at it and go, oh, wait, that may work because the rate law is NO squared times O2. But wait a minute. We don't have any O2. So that means that doesn't work. So we're going to keep going. So this is 3 steps. So your NO2s cancel. Your N2O3s cancel. Those are both intermediates. So we're left with 2NO plus 2O yields 2NO2. So wait a minute. Wait, this won't work. Because remember, O2 is not the same as 2O. So this doesn't even work for that one. So we don't even have to worry about the slow step because it's not going to sum. Now, if you had happened to have glanced ahead at the slow step before you added them together and said, wait, into O3, that's not in there, you'd be okay to do that too. All right. So the next one, we'll move forward to the pink. All right. We're going to add them together. We have the NO3 going away. We have 2NO plus O2 yields 2NO2. So that works. But our rate, according to the slow step here, is K, NO3, NO. None of which appear in our rate law, so that one doesn't work. So here we go again. The O's cancel, so we have 2 no's plus O2 yields 2NO2. And our rate is equal to K times NO. Hey, this is looking pretty good, times O2. So we have NO and O2, but according to our rate law, we need 2 of the NOs. So this one's not going to work. So let's look at the last one. Look, it's one step. It matches the equation. The rate would be equal to K times NO squared, O2. So guess what? It matches. It works. The only one that works here is the F one. Okay? Now, there are a couple really good reaction mechanism problems in your text. I highly recommend you look at them and understand the pieces parts. And so look over those. But they're really simple. Do they add up to what you need them to add up to? And is the slow step equal the experimental slow step?